Hey everyone, welcome to another video. Today we're going to be working through an AP Calc BC free response question. I genuinely like these questions because I think they're really cool and integrate a lot of information from across different parts of differential and integral calculus. And they're just fun to do when you remove the pressure of writing them for writing an exam, right? So let's go ahead and talk about this now. So just for your reference, by the way, this is from the 2018 AP Calc BC exam. It's question 3. It's on the non-calculator portion. So I will post a link to where I found these. They're just on College Board's website, so you're welcome to check those out at your leisure as well. Okay, so let's go ahead and take a look at this. So we're given the graph of this function g over here, and we're told that g of x is a continuous function, which is the derivative of some other function f of x. Right? Doesn't actually tell us anything about f of x, but we're just told that g of x is the first derivative of f of x, right? So that's given to us. We're also told that g of x is piecewise linear for this interval here from -5 to 3, not including 3, and that it takes on this quadratic, which is 2 times this quadratic here. It takes on a quadratic from 3 to 6. Great, so now we're being asked a couple of questions. So firstly, given that f of 1 is 3, what is the value of f of -5? Well, once again, remember we're being asked about the function f of x, about which we don't actually know anything, right? We only know that the derivative is g of x, and we were told there'll be this information about g of x, right? So how do we apply the information about the derivative to tell us information about the original function? Well, that's where we use an integral, right? So we're going to have to make use of an integral here. So we've got what we're looking for, which is f of -5, right? And what we know is that f of 1 is 3, so we'll start at f of 1, and then we'll tag on this integral from 1 to 5 of g of x, which is f prime of x, or the derivative dx, right? And remember, we start at 1, and then this integral here represents the net change from 1 to -5. Right? So that's what that integral does for us. However, notice that, that should be a -5, my apologies. However, notice that my lower bound in this case is actually greater than my upper bound. That can be a little bit annoying to deal with at times. So what I'm going to do right off the bat is I'm going to switch this sign. I'm going to switch these signs. Right? I'm going to switch these bounds, excuse me. I'm going to switch these bounds and then add on a negative sign there. Okay, which is perfectly legal. So we have f of 1, which we know is 3, right? And then we're going to tag on a negative sign times the integral, not from 1 to -5 anymore, but the integral from -5 to 1, right, of g of x dx. Again, the reason for that is just because I don't like dealing with the bounds like this. It's much easier to work with when they're like this. Okay, let's go ahead and take that integral now. So if we come up here, let's see what we can do. So you'll notice though that we're not actually told what g of x takes on from -5 to 3, right? Or this interval here, which we're interested in, right? We're only told that it's piecewise linear. So therefore, we can't actually use anti-differentiation to evaluate this integral. We're going to need to use something different. As it turns out, since we're told that this is linear, we can actually go ahead and use signed areas. Right? Signed areas. Yeah. And by signed areas, what I mean is we just come up to the graph over here, and we just literally use this shape right here to find the area under that curve on the given interval. Right? So let's go ahead and do that. Right? So we're going to start at -5. We're going to find the area under this curve all the way from -5 up till 1. Okay, so we're going to find all that area. Okay? So let's break this up into a couple of shapes. Right? So we have, if we break this up like this, we have, so we have a triangle and a square here, right? If we break it up like that, and we have on this side another triangle. Okay, so if we take the area of all those pieces add them together, we'll get our final answer. Okay, so for the square here, oopsie daisies. So for this square here, yeah, my area is going to be just the width times the height. This is a 3 by 3 square, because we go 3 units. So the area is just going to be 3 times 3, which is 9. Okay. This triangle here, we're going to use the formula 1/2 base times height. The base is 1. As you can see, it goes from -1 to -2. The height is also 3, same as square there, so it's just going to be 1/2 1 3, which comes out to 1.5, or 3/2. Sweet. Next thing we want to do is find the area of this triangle here, right? So we're once again going to use 1/2 base times height. So we'll have 1/2. Our base this time is also 1. And our height this time is going to be 2, right? So height is going to be 2. And this 2 and that 2 are actually just going to cancel out. So we're just left with an area of 1. Okay. Now you might be wondering why I colored all these areas differently. And that brings me to one aspect of the whole concept of signed areas that we need to talk about, right? And that is that when you have area below the x-axis or area above the x-axis, there's a difference in how we treat those, right? So area below the x-axis, we always assign a net negative sign to, right? We always assign a negative sign to any areas below the x-axis. Likewise, anything above the x-axis, we assign a positive sign to, right? So that's why I've colored these things differently, because any areas below the x-axis we want to treat as negative, anything above we treat as positive. So yeah, bearing that in mind, let's sum all these together and get our final answer for this integral. Okay, so if we do that, we will have 3 minus -9, right? We'll have -9 minus 1.5 from this guy up here, and then plus 1. Okay? And now we just need to add these all up and we'll have our final answer. So minus 1.5 plus 1 is just minus 0.5. -9 minus -9 minus 0.5 is just going to be -9.5. And now bear in mind, we have this other negative sign out here. So we'll really need to be, so we're really going to be adding. So if all of this comes out to -9.5, since I have this extra minus sign out here, I'm really adding 9.5 instead of subtracting. So 3 plus 9.5, this is going to give me 12.5 as my final answer, which, if you want to be picky about using fractions, is just 25/2. Okay, and there's your final answer. Wonderful. So that's part A. Let's talk about part B now. Okay. Part B, we're now being asked to evaluate the integral from 1 to 6 of g of x dx. Very similar to what we did up here. Okay, so we want to find the integral from 1 to 6 of g of x dx. So let's go back up and see what exactly g of x is for that interval. Now there's something interesting that happens here. We're starting at 1, right? We start at 1 and we end at 6. Notice that on this interval, my function actually switches what value it takes, right? So from -5 to 3, it's this piecewise linear thing, but from 3 to 6, it's this quadratic here. So it's switching what value it takes on. So we need to take that into account in our integral, right? So we know that this function switches what value it is at 3, so we're going to need to break our integral up into 2 separate integrals, right? As follows. So this is going to be equal to the integral from 1 to 3 of g of x dx plus the integral from 3 to 6 of g of x dx. Okay? Hope that makes sense. Yeah? So, and again, this piece right here is in that linear area, right? This piece right here is in that linear area, so we can evaluate this guy using a signed area. Whereas with this guy, we actually are told what the function is, so we can just use the regular anti-differentiation method. Or anti-differentiation plus fundamental theorem of calculus part 2, if we want to be a little more picky. Okay, so that's that. So let's go ahead and do this guy first now. So if we come back over here, I'm going to erase what we've got here just so we have some more space. Okay, just to clean things up a bit. So we're interested in the area from 1 to 3, right? So we're interested in this area right here. That's just a 2 by 2 square, right? So the area is just going to be 2 times 2, which is just going to be 4. So that's our answer for that integral. So yeah, that's basically what that's going to be. So we have 4. And then on this side, for that piece, we're going to have the integral from 3 to 6 of 2 times, what is that? It's, yeah, x minus 4 squared dx. And this right here will require a little bit more work. Okay, so there's a couple of different ways. So there's a couple of different ways in which you might approach this integral. So you could FOIL it out and anti-differentiate each piece, or you could use a u substitution and go from there. Both are fairly straightforward, but since the foiling is just a little bit more algebra, we're going to go with u substitution in this video. But again, just know that both methods are equally correct. So let's do a u sub here. So we're going to pick u equals x minus 4. Pretty nice u sub there. So we're going to get du equals just dx, because the derivative of x is just 1. And now at this point, I actually have another choice here. I can choose either to keep my bounds in terms of x, in which case I will have to plug back in for x when I finish taking my when I finish evaluating my antiderivative, or I can switch my bounds to the u world right away, and then I don't need to plug back in. I'm going to switch my bounds over to the u world, and that way I don't have to plug back in for x when I'm done doing my anti-differentiation. Right? So let's go ahead and do that. So when x is equal to 3, this gives me that u equals, is going to be 3 minus 4, which is minus 1. Likewise, when x is equal to 6, that tells me that u is going to be 6 minus 4, which is just going to be a plus 2. And now I can use these as my new bounds of integration. Okay, let's come down here and put this all together. Right, so now I'm going to have that 4 still carries over for the previous part. Right, so then we're going to have the integral not from 3 to 6 anymore, but from minus 1 to 2 of 2 times u squared du. That's a pretty nice one to actually evaluate. So what we're going to end up with is we'll have 4 plus, we're just going to have a reverse power rule there. So that's going to be 2/3 u cubed evaluated from -1 to 2. Now, if you did not switch your bounds over to the u world, right? If you did not do that, you would need to plug back in for x now, and then use your original bounds to evaluate. Either process will give you the exact same answer, but it will be a slightly different path, right? But this is what we've chosen, so we can just go ahead and evaluate these right now, right? Since we already switched our bounds over. Okay, so this piece right now, if we look at that separately, is going to come out to, if we plug in the 2, that will be 2 cubed, which is 8. 8 times 2 is 16, so we have 16 over 3 minus, if we plug in -1, that's just going to be -2/3. Yeah, cool. So now that we've got that, we just add these two together because the negative signs cancel. So we're going to get 18/3, which is just going to come out to 6. So the final thing we have right here is just going to be 4 plus 6, which gives us 10. So our final answer to this whole integral is just 10. Lovely. That was a really cool question. All right, now let's look at part C. So part C is asking us for this interval, right? For for the interval of this graph, we're being asked where this function f of x is both increasing and concave up. What do those words increasing and concave up mean to us in terms of calculus? Well, increasing, right? That's where f prime of x is greater than 0, right? Concave up, likewise, is where f double prime of x is greater than 0. But once again, we run into the same caveat where we don't actually know anything about f of x, right? What do we know stuff about, though? Well, we do know stuff about g of x, right? So how did these two things come into play in terms of g of x? Well, g of x is for f prime of x. G of x is equal to f prime of x. So basically, when we say f prime of x is greater than 0, we're really looking for where g of x is positive, right? We're looking for where g of x is greater than 0. Likewise, when we look for where f double prime of x is greater than 0, we're looking for where g prime is greater than 0. Okay? All right, so now let's come up here to the graph and see what we can make of it. Okay? So I'm going to just quickly erase this guy to give us some more space. But let's see what we can make of this. So we're looking for places which satisfy these two criteria, right? So where g prime of x is greater, where g of x is greater than 0 and g prime of x is greater than 0. We can eliminate some things right off the bat, right? So we can eliminate this entire piece over here, right? This is since g of x is less than 0 here, so that this doesn't work. We can also eliminate this piece over here, right? Since g prime of x is less than 0 there, right? Because if you look at it, the g of x is decreasing there, so g prime of x is less than 0. We can also eliminate this part, right? We can also eliminate this line here, this one line here, because over there, g of x is greater than 0, but g prime of x is equal to 0. So that doesn't work for us here, right? So we can eliminate all three of these regions. So we can eliminate all three of these regions, and now what we're left with is just these two pieces here. So we have this line here, and we have this other piece over here. Okay. What are the x values? Well, if we clear away some of this rubble, let's make that. If we clear away some of this rubble here, we'll see that that interval is going to be from 0 to 1, right? We're going from 0 to 1 and from 4 to 6. Those are our point. That's going to be our interval, right? So we can come down here and say, all right, so if we can come down here and say the intervals are going to be from 0 to 1 and from 4 to 6. But they ask us to explain why. So let's go ahead and explain. So we can say that on these intervals, right, g of x is greater than 0. And remember, g of x represents f prime of x, right? And g of x is increasing, which implies, this thing right here implies that g prime of x is greater than 0, which doubly implies that f double prime of x is greater than 0. Hence, right, hence, f of x is increasing. Sorry, my handwriting there was really terrible. Is increasing and concave up on these intervals. Sweet. So that's part C. Last but not least, we will work on part D. And that one right here tells us we want to find the x-coordinate of each point of inflection on the graph of f, right? So once again, I'm going to go ahead and erase all this just to make things a little bit easier for us. Okay, so we're being asked to find the point x-coordinate for each point of inflection, right? Points of inflection, remember, are places where f double prime of x switches signs. Right? Switches signs from positive to negative or negative to positive, right? But since we're not talking about f double prime of x, we only know about g of x, so we're looking for where g prime of x switches signs. Okay. So to help me out with this, I'm going to make a little chart here, and I'm going to track exactly what g prime of x is doing at every given interval here, right? So that place looks interesting. So let's make a line there. Okay. So on this interval from over here, g prime is just 0, right? From -2 to -1, it's positive, right? Because g of x is increasing. On this interval here, from -1 to 0, it's 0. Right? Over here, once again we're increasing. Over here on this interval here, we're 0, and now here we're decreasing, and now everywhere else we're increasing. Right? So 0 increasing, 0 increasing, 0 decreasing, increasing. So out of these, which of these satisfies our criteria for being where g prime of x switches signs? Well, that's going to be down here, right? Because all of these, like switching from 0 to something doesn't really count. So we want to find where it switches from positive to negative or negative to positive. That's the only place where that happens. So our answer is going to be x equals 4, right? So let's come down here and tell them that. So it's going to be x equals 4. And why is because g prime of x, which is the same thing as f double prime of x, switches signs from negative to positive. From negative to positive at x equals 4. Wonderful. And yeah, that brings us to the end of this problem. I will check the answer key before I post this just to make sure I've got everything right, but I think I have everything down here. And yeah, that's basically what your average AP Calculus BC FRQ is like. So I hope you guys had fun in this video. So please do let me know if you'd like to see more of this from my channel. They're generally kind of fun to do, and yeah, it'd be great to make more of these. If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time!